Hey folks, today we continue with kinetics and equilibrium, and we're specifically talking about equilibrium. Look at that picture below you. Does it kind of bring something to mind for equilibrium? Let's talk about that in just a moment. Most reactions, when we think of them, go to completion, or pretty close to completion. The reaction continues until one of the reactants, the limiting one, is completely consumed. And that is the way we think. For example, if we have a fire going, right, we expect all the wood to burn, and we expect there to be no wood left. That's our limiting reactant. We didn't run out of oxygen, but we did run out of wood. When we bake a cake, we don't expect the middle of it to still be liquid. We expect the entire thing to have gone through the chemical reaction and to have converted into a nice cake that's still moist, but that is dry and not liquid. Okay. When we burn hydrogen and oxygen, which are coming out of this fuel tank in here, out the back of the space shuttle, we expect the hydrogen and oxygen to completely burn. All right. When we have the solid propellant coming out of the back of these things, out of the back of these boosters over here, we expect them to completely burn. When we make concrete, we expect all of the concrete block to react and go from a liquid or a whatever it is into a complete solid. Okay. And that is what we expect to happen. We don't expect this part of the concrete block, let's say, to remain kind of soft. We expect it all to become hard. Okay, that's the concept of reactions. We expect them to go to completion, and most of them, the way we look at them, do. Now, most of these reactions have opposites as well, and these go to completion as well. So, for example, back here out the back of the space shuttle, I'm taking H2, and I'm adding it to O2, and I'm coming up with water. Now, that's not a balanced chemical reaction. Now it is. Right? That's what we see on the left. But what do we see on the right? On the right, we see some water, which is what we see down here. This is all water. And it is breaking apart into H2 and O2. Actually, I should probably write it O2 and H2 plus H2. And there are two of those, and two of those. It's a balanced chemical reaction. So over here, we've got O2. And over here we've got H2, and how do I know that? I notice that there's twice as much hydrogen as there is oxygen. Ah, yes, because that's 2H2 instead of O2, so there's twice as much hydrogen as there is oxygen. So I can take that reaction where I'm combining hydrogen and oxygen to make water, and by the way, it makes a lot of heat, whereas I could take water and I could split it back apart using a process called electrolysis back into its component parts, which are hydrogen and oxygen. So these reactions are completely opposite, and I can reverse them. Now, let's think about what happens when we go out and we look at trees. Right? Well, what are trees doing? Well, trees are taking carbon dioxide out of the atmosphere, and they're adding to it water out of the ground, right? And they are producing sugar, which is C6H12O6, and they're producing oxygen gas, which we breathe. And I can balance that reaction. And that's what you see going on down here. All right. What do you see going off here? Well, you see a person breathing. Sorry, that was tough to show. And that's respiration. And that is the exact reverse of this equation you see up here. So if I took the arrow and flipped it back and made it go the other way, that's what I have over here. I have it going the opposite direction. So again, these reactions are going to completion, and they are perfect opposites of each other. Some reactions, however, never finish. They kind of go part way, and then they don't go any further. Okay, and they reach this state of equilibrium that we talked about. So if we look at equilibrium, the concept here is we look at these people, and they're pretty much equally balanced on top of this seesaw, teeter-totter, whatever you want to call it. So as a result, the thing stays pretty level. Right? So it is balanced. So that's what equilibrium is all about. It's all about a state of balance. Of the reaction is not going in one direction or the other. It's just completely balanced. Unlike this, which is not equilibrium, here we have one side that clearly is heavier than the other. So if this little guy over here, if he were to move forward just a little bit, then the weight of this guy would come down, and so we could get him down. So anyway, This is definitely not equilibrium. All right, the concept of equilibrium, and we look at a dynamic state of equilibrium, which is the exact balancing of two processes, one of which is the reverse of the other. So we have all of these people over here on the right going up the escalator. We have all these people over here coming down the escalator. And the concept is, if these two processes are equal, if the number of people going up and the number of people going down are always the same, then the number of people we have up here on the second floor is going to stay the same. Right? Now, we're constantly adding people, and we're constantly taking people away. But the number of people up on the second floor remains the same. Okay? That same kind of concept can work with water. We talked about vapor pressure. And we talked about vapor pressure being in equilibrium between evaporation, that's the water going up into here and evaporating, and condensation of the gaseous water going back to become a liquid. Change is happening in both directions, and it's happening simultaneously, and it's happening at the same rate. So as a result, the amount of water vapor you have up here in the top of this bottle remains constant. And when we talked about vapor pressure at certain temperatures, that is what we were talking about. Okay? It's at a state of equilibrium between the water evaporating, the liquid water evaporating, and the gaseous water going back and becoming a liquid. We call this dynamic equilibrium. Now, we use the word dynamic because while the concentration up here is constantly changing, there is something going on, which is dynamic. The change is happening in both directions simultaneously. Stuff is evaporating, stuff is condensing. So, since it is the same rate, we call this dynamic equilibrium. Now, when we have chemical equilibrium, this is when the rates of the forward and reverse reactions are equal. So we've already shown you a couple of forward and reverse reactions, but at chemical equilibrium, at chemical equilibrium, yes, no net change occurs in the actual amounts of components of the system. So nothing changes. Now we call these reactions reversible. So a reversible reaction, you should write this down, is the conversion of reactants to products and the conversion of products to reactants, and they are occurring simultaneously. One is going this way, one is going this way. And when those rates are the same, you have achieved equilibrium. Now, you don't achieve equilibrium immediately, but once those rates are the same, once they've balanced out, equilibrium has been achieved. Now, let me make one side note here. The addition of a catalyst speeds up the reaction, but it does not cause a shift in the ratios of products to reactants. In other words, just because it happens faster, that simply means it gets to equilibrium faster, but it didn't make equilibrium change. So, for example, if we think of just a reaction, and okay, I'm just going to put reactants over here, and I'm going to put products over here, right? And if our equilibrium position is there's 10% of these left when we reach equilibrium and 90% of these when we reach equilibrium, so we have a reaction going both directions because we reach equilibrium, right? If I put in a catalyst, it simply makes us to get to this point of 10%, 90% faster. But we still get there, and that's still the equilibrium position, whether we add a catalyst or not. All right, let's look at a particular reaction. First thing to do is note the arrows. Notice you have an arrow going forward and an arrow going backwards. This is what indicates to you that we have a reversible reaction, and that it is at equilibrium. So your forward reaction is going this way. So you'll notice that this is what we see as a forward reaction, and we have an arrow there. But we also have a backward reaction, which is the same reaction with the arrow going in the opposite direction. And that's what we call the reverse reaction. So we actually have two reactions going on. The sulfur dioxide is combining with the oxygen to make sulfur trioxide, but at the same time, some of the sulfur trioxide is decomposing back in the other direction to make sulfur dioxide and oxygen. So let's look at this graphically. If we start, if I take these guys over here, that's what I have over here. I only have oxygen, which is O2, and I've got some SO2s in here as well, right? And that's what I'm starting with. and it's a pure mixture of these two things. Right? Well, what happens is some of it converts into SO3. You'll notice there's an SO3, and there's an SO3, and there's an SO3, and there's an SO3, but you'll notice we still have some oxygens and SO2s floating around. We have reached a state of equilibrium, right? Where if, for example, these guys combine, then some of these are going to decompose back into the sulfur dioxide and oxygen. Similarly, had I started with a complete box or container of SO3s, all of these are SO3s, sulfur trioxide, then it is going to move the opposite direction so that some of them break up. So either way, we're going to end up at this equilibrium position in the middle where we have some sulfur dioxide, some oxygens, and sulfur trioxides. So our equilibrium position, this means the relative concentrations of the reactants and products at equilibrium constitute the equilibrium position of the reaction. In other words, when we have to get to equilibrium, which is here, that's our equilibrium position of the reaction. So that is eventually where we're going to get. It doesn't matter whether we start with SO2 and oxygen. It doesn't matter whether we start with SO3. We are going to end up here in the middle with a certain ratio, if you will, of reactants to products. So let's look at how this works. Let's say that we start with just SO2 and oxygen. So at time 0, we have a certain amount of SO2 and we have a certain amount of oxygen, right? And we have no SO3. Well, as the reaction proceeds, the reaction is going to proceed in this direction because we're starting with a very high concentration of SO2 and oxygen, and we move towards creating SO3. So that's what happens. That's this yellow line going up here that you see, right? But when we're all done, notice how the levels level out, right? So we end up with a certain amount of SO3, but you'll notice the reaction didn't go all the way to completion, because if it had, 2 SO2s produce 2 SO3s, so I would have had SO3 up here. But notice I don't. I've only got so much SO3 because I still have some SO2 and oxygen that are not converting. Now remember, we're in a state of dynamic equilibrium. So some of these SO2s and oxygens are combining to make SO3s, but some of the SO3s are breaking apart, are decomposing back into SO2 and oxygen. That is all happening at the same time, so we have reached a state of equilibrium. What happens if we try it the other way? What happens if we start with all SO3s? Well, if we start with all SO3s and no oxygen and no SO2s, again, over time, we're going to produce some SO2 and some oxygen, but then we're going to hit this equilibrium position again where we stop. And notice that our graph here is showing that it's not changing. We've reached a state of dynamic equilibrium where some of the SO3 is decomposing and some of the SO2 and oxygen that we just created is turning right back into SO3. Let's put those two graphs together on the same page, and you'll notice that the SO3 levels on both graphs and the SO2 and oxygen levels on both graphs are the same. So another way to look at that is to say our forward reaction and our backward reaction eventually get to some equilibrium state. And that is what our rate is when we're finally done. Okay? So we get to that equilibrium state, that equilibrium position, where we have some SO2 and oxygen present and some SO3 present, and it's not changing. All right, what happens when we combine hydrogen and oxygen? Well, almost all reactions are reversible to some extent. Did every single molecule of hydrogen react with oxygen and make water? The answer is no. There is some hydrogen sitting out there in the atmosphere. So when we're breathing air in, air is mainly nitrogen and oxygen. But there's also carbon dioxide in it. Why? Because I just breathed out carbon dioxide as I was talking, as I was breathing. Okay, I exhaled that. So it's in the atmosphere all around me, so I'm breathing some of it back in. Okay, so I am breathing some of that carbon dioxide back in. But there are many, many other gases in the atmosphere, and hydrogen is one of them. So it does not spontaneously react with oxygen to make water, right? It needs enough energy to do that. It needs the right orientation to do that. And what we have is an equilibrium reaction where most of it goes to water, but there's still some of it that decomposes naturally in the atmosphere to hydrogen and oxygen. So even though the vast majority is water, there's still some of it that is hydrogen and oxygen. So we do have most of it going this way, and we have a little bit of it going back the other way. So we might draw it where we have one arrow that's longer than the other to indicate to us that most of it becomes water, but only some of it goes back to hydrogen and oxygen. Okay, so we might have, when we look at a reversible reaction, we might have arrows that are not the same length. Now, how do we compare the different reactions to see where we are with equilibrium and what do we have most of? Well, that's the next podcast. So that's what we're on to. Go ahead and do the worksheet for this one, and let us know if you have questions, and we'll see you in class.